Today in calculus, we're going to talk about lesson 64. And we are talking about the derivatives of inverse trig functions and which ones are worthy of memorizing. On the front page, we're going to kind of take a brief look of what the derivatives of these are. In our examples on the front, we're going to look at how we can find the derivatives of the inverse trig functions if we don't remember them. And on the back side, we'll talk about the two that are probably your best bet to have memorized. So if you just kind of look briefly at the chart up above, go through and give some derivatives. I'll write them in a little bit neater form when we go through and do some of these. But for instance, the derivative of sine inverse of x over a of course being some constant, is, and notice on top is just a differential dx, so that would be the equivalent of having a 1 there. So the derivative of sine of x over some number is 1 over the square root of the number squared minus x squared. You'll notice cosine is the same except just a negative. So on top, that would be equivalent to saying negative 1 over the square root of a squared minus x squared. Tangent inverse, instead of having a 1 on top, you'll notice that there is a constant of a on top. And it's a over the square root of a squared over x squared. Excuse me, I think I just said square root. There is no square root in tangent. Cotangent is just the same, except it's a negative a over a squared plus x squared. And then secant and cosecant, change it up a little bit again. Secant inverse of x over a is a over x square root of x squared minus a squared. And cosecant inverse of x over a is negative a over x square root of x squared minus a squared. Now, as we look at our first example, we're given that y equals arc sine of x over a and asked to find y prime. Again, we're not using this chart up above, we're going to develop it. First of all, remember that arc sine of x over a, another way of writing that is saying sine inverse of x over a, where we use the inverse notation with the little negative 1. Now, if we want to write this in another way, remember that what happens with an inverse. And when you look at the inverse, it takes the input and the output values and it switches them. So here we have sine inverse. If we want to get just to sine, we can take our input and output values and switch them. So instead of saying sine inverse of x over a, it's going to be the sine of y, and then it's going to, instead of equaling y, it's going to equal x over a. Now, I'm going to go ahead and do kind of a side note here. This will become important later on down in our problem. But based on the trig function, sine of y equals x over a. I'm going to draw a triangle over here to the left. And as I said, it will hold importance later on here in this problem. So I'm going to draw a triangle. And the sine of y equals x over a. So if you remember sine is, as in SOHCAHTOA, opposite over hypotenuse. So the sine of angle y, so I'm going to use this angle right down here to be y. The sine of angle y is equal to opposite over hypotenuse. So that is going to be x over a. And then the question, again, that we'll need to know later, I'm trying to set us up for it, is what is this piece right here? And how can we find that missing piece? Well, of course, you know that this is a right triangle, and so we can use Pythagorean theorem. And if we use Pythagorean theorem, I'm going to call this side down here b, I guess. And so I'm going to say b squared plus x squared equals a squared. If I'm trying to solve for b, I'm going to start by solving for b squared. So b squared is a squared minus x squared. And if b squared is a squared minus x squared, then we know that b is the square root of a minus x. And I mention that now because that means this side down here, the question mark side, is I said that wrong. It should have been the square root of a squared minus x squared. I hope you are yelling at me during this video to catch my mistake, because that was a horrible mistake. So the square root of a squared minus x squared is this side down here. Okay. As I said, the triangle is kind of a side note. We're going to use it here later on. So if we go back to our problem at hand, we have sine of y equals x over a. Our goal is to find y prime. So we're going to take the derivative. Now, in order to take this derivative, this is not explicitly solved where it's y equals now. So we're going to have to use implicit differentiation, where you take the derivative of each piece and tack on the appropriate dx or dy. So, the sine of y. What is the derivative of the sine of y? And that, of course, is cosine of y times the derivative of what variable? The derivative of y is dy. Then we're going to do the derivative of x over a. Keep in mind a is a constant, so this is like saying 1 over a times x. And the derivative of 1 over a times x is going to be 1 over a, and then times the derivative of the constant, or of the variable, which is dx. Now, if you recall, we're trying to find y prime. So another form of finding y prime would be finding dy dx. So if you take your current equation and you solve it for dy dx, I already have dy on the left, so I'm going to keep my dy on the left. And then I'm going to divide my dx to the right. So both sides are divided by dx. The dx on the right cancels, and that becomes dy divided by dx on the left. On the right, I still have 1 over a, and then coming from the left, I have to divide by cosine y. So to divide by cosine y, I'm going to write it as 1 over cosine y to indicate that we divided by cosine y. Now, as we look at our derivative, it's a derivative of y with respect to x, which means everything really should be in terms of x, but you will notice cosine y is not in terms of x. So, we have to do a little bit more work to finish finding our derivative. I'm going to move up here to the side where I have a little bit more room. So we currently have dy dx equals 1 over a is just constant, so that's good, times 1 over cosine y. There was a reason I did that triangle earlier. Cosine of y. So that means we're looking for the cosine of angle y. Well, if you recall, we already have angle y right here, yes? So now we're trying to find the cosine of that y, of that angle. So if you remember, cosine is adjacent over hypotenuse. Well, our adjacent side is that square root of a squared minus x squared, and then the hypotenuse is a. So in this denominator over here, I'm going to write the square root of a squared minus x squared all over a. And now, it's just a matter of cleaning this up and finishing it up. Dy over dx, I'm still going to say 1 over a. It's 1 divided by that fraction in red, and 1 divided by a fraction is going to be the same thing as multiplying by the reciprocal. So flip the a up to the top, and it's a over the square root of a squared minus x squared. You will hopefully notice that our a values can cancel, and we are down to dy dx equals 1 over the square root of a squared minus x squared. And that is your derivative of sine inverse of x over a. Okay, they're all going to work similarly here. And so we're going to practice with at least cosine and tangent to try and make sure that you have a confident idea of how you can do this on your own before we practice using these some on the backside. So, pause video where you need to, of course. But for the moment, I am moving on to example 2. Example 2 gives us y equals arc cosine of x over a, find y prime. Out of habit, and I think it's just more what I'm comfortable with, I tend to automatically rewrite this as cosine inverse of x over a. Now, if we're going to take this out of this inverse, so in other words, taking it from cosine inverse to cosine, what do we do with our input and output? They will switch. And so we're going to say the cosine of y is equal to x over a. You can do it now, or you can do it later. But again, we're going to have to talk about a triangle. And I'm going to kind of shortcut. I'm not going to write out as many details this time because I have confidence you guys can do Pythagorean theorem in your head. So the cosine of y this time. So I'm going to call this same angle y. Cosine of y is equal to x over a. So remember that is adjacent over hypotenuse. So adjacent over hypotenuse. So there's my x and a. We need to have a value. This triangle is indicating. We need to have a value for that vertical side. And if you think about a squared plus b squared equals, let me back that up. I said it wrong again. B squared plus x squared equals a squared, and you try and solve for that b. You end up with a squared minus x squared and the square root of it. So this is going to be the square root of a squared minus x squared on that third side. Okay, back to working our problem. The derivative of cosine of y is going to be negative sine of y. Again, we're doing implicit differentiation, so you have to times by the differential, dy, equals the derivative of x over a. So again, think of that as 1 over a times x. So the derivative is 1 over a times dx. Again, I'm trying to solve for dy dx. So keep the dy on the top. Divide the dx to the right. Or to the left. Keep the 1 over a on the right. And divide the negative sine y. So we're going to have 1 over negative sine y. Again, if we're doing the dy dx, we need our answer all to be in terms of x. And right now we have a y. So we're going to have to replace that negative sine y. So, continuing working, dy dx is equal to, we still have 1 over a times 1 over negative sine y. So it's going to be the negative of sine of y. So if you look at y, angle y there, and we need to talk about the sine of that angle. And the sine is going to be opposite over hypotenuse. So the square root of a squared minus x squared over a. And then, of course, we already had that negative in there. Okay, from here it's a little bit of cleanup. Dy dx equals 1 over a times, I'm going to say the negative of, and again it's 1 divided by that fraction, so flip the denominator up top, and it's a over square root of a squared minus x squared. In the final cleanup, you will notice, of course, that the a values will cancel. And we are left with the negative of 1 over the square root of a squared minus x squared. This would be the derivative of cosine inverse. Very similar to sine inverse, different by a negative sign. Okay, I want to look at one other here, and that is tangent. Very similar setup to last time, just difference, of course, in how everything works out. It's already written this time as tangent inverse instead of using arc. So if y equals tangent inverse of x over a, okay, take it out of inverse form. And so then we're going to have the tangent of x over a is equal, no, that's not what we're going to have, is it? That's what we already have. Sorry, flip those inputs out and outputs. So the tangent of y equals x over a. Okay. If you want to go ahead and make your triangle here, that would be a good time to do it. So if I make my triangle here, okay, I'm going to put y in the same corner, being consistent. Tangent of y is equal to x over a. So if you remember tangent, that is opposite over adjacent. So x over a. So if you use your Pythagorean theorem, that hypotenuse squared equals a squared plus x squared. So that hypotenuse is equal to the square root of a squared plus x squared. Okay, hold on to that thought. We'll use it later, of course. So, derivative of tangent. Y, derivative of tangent, this is one to memorize, you know it. Derivative of tangent is secant squared y with respect to y means times dy. Derivative of x over a still is 1 over a times dx. Again, trying to solve for dy dx. So I'm going to keep my dy on the left, going to divide by dx on the right, or on both sides. On the right, I'm going to keep my 1 over a, and then I'm going to divide by secant squared y, so 1 over secant squared y. There are a couple of different ways you could deal with this. Similar to the last one, we can do 1 over, and we can substitute in values for secant squared y. I'll be honest, my brain does not work quite as well with secant. But what do we know about secant? And hopefully you're telling me that secant is the reciprocal of cosine. And so if this is dy dx already equals 1 over a times 1 over secant squared y is going to be equivalent to just cosine squared y. So I would right there go ahead and get rid of the secant because I'd do much better off working with my main 3. And so changes to cosine squared y. Now, of course, it's still in terms of y, which is a problem. And so we're going to continue over here and substitute in appropriate values. So dy dx is equal to 1 over a times, and then cosine squared y. So remember, cosine of y, cosine is going to be adjacent over hypotenuse. So a over the square root of a squared plus x squared. Now keep in mind it was cosine squared, so I'm also going to square this fraction. Okay. Do the cleanup. Dy dx. Let's see. It's 1 over a times a squared over, what happens when you square square root? You just get a squared plus x squared. Now, keep in mind, important detail, we can't cancel the a squareds because the a squared in the denominator is part of a squared plus x squared. However, you can cancel a single factor of a. This a in the denominator can cancel with 1a from the numerator. So, final answer, dy dx is equal to 1a, or in other words, a over a squared plus x squared. And that is your derivative, of tangent. Excuse me, tangent inverse. Okay, now I am at 20 minutes on this video already, and I still want to do examples 5, 6, and 7 on the back. So I think what I'm going to do, I'm going to go to page 2 first of all. And as I go to page 2, I think you've probably gotten the idea of how all these work. I'm going to just go ahead and write out the answer for example 4. If you want to try and go through and solve that, you can, and I can always help you sometime in person. But I will tell you that if it's cosecant inverse, the derivative of cosecant inverse of x over a works out to be negative a over x times the square root of x squared minus a squared. Okay, I'm sure there is probably, I haven't looked recently to remember, there's probably a proof in the book that would also help you if you are curious about how that works out and can't get it to work out right. Okay, part B, what to memorize. Okay, guys, 2 big ones I mentioned earlier. The derivatives of sine, inverse sine, and inverse tangent tend to appear more frequently. And so those are the 2 that is the best to have memorized. If you're concerned about cosine, just realize cosine is just a negative sign different from sine. So notice here, derivative of sine inverse of x over a is 1 over square root of a squared minus x squared. And derivative of tangent inverse of x over a is a over a squared plus x squared. Those are the pieces you need to know. Don't worry about the dx's there. Worry about the other pieces is what would be my thought. Okay? And do remember, you have to, the setup we have to think about on on all of these is always that they are x over a. And I will help you walk through that a little bit. So let's look at example 5. If y equals tangent inverse of cosine x, what is dy dx? So of course we're being asked to find the derivative of, notice what is my main function, and my main function is tangent inverse. Now, what is the insides? That's the important part to remember, because if you look up in our examples or in the formulas, the insides have to fit the form x over a. Well, my insides is cosine x. And so what is cosine x as a fraction? And like anything, when I ask what is as a fraction, you can always put it over 1. And so when we talk about x over a, my insides being x over a, in this case, it's cosine x over 1. So whenever I fill anything in to my formula, in place of x, I'm going to throw cosine x. In place of a is just going to be 1 on this case. So, let's look at this one. If y equals, so derivative of y, I'm going to write dy dx. Tangent inverse of something. Well, tangent inverse of something, look up there, is a over a squared plus x squared. So, remember my a value over here, it's your denominator value, which if we just have cosine x, the default is a is 1. So we're going to have 1 on top, and then it's over a squared plus x squared. Well, again, my a value is 1, So that's going to be 1 squared plus x squared. My x value is cosine x. So we're going to say cosine x squared, or cosine squared x, I should say. Now, like any other piece of calculus, when we are taking a derivative, we always have to consider what our inside was. And when we're doing the derivative of tangent inverse of cosine, that means we're doing the derivative of tangent inverse of something, which means you always then have to do times the derivative of something, which in this case means we're doing the derivative of what was our x value, and it was cosine x. And so out here we're going to do the chain rule. What is the derivative of cosine x? And that is negative sine x. And I will even write that in, that this was the result of chain rule. There's not really a lot of cleanup I can do other than put it as one fraction. dy dx, and I'm going to put that negative sine x on the numerator. So negative sine x over 1 plus cosine squared x. Okay, and there's a part of me that's trying to look at your faces right now and say, are there questions? So hopefully you guys will catch me in class for questions on the following day, if necessary. Okay, so let's look at example 6. Y equals arc sine of 2x, find y prime. Now, first of all, if it helps, remember arc sine. Sorry, my pen just turned off. Arc sine is the same as saying sine inverse of 2x. Also, if we always want to think about the inside, so we're going to be doing the derivative of sine inverse of something, the insides of being a fraction, 2x as a fraction is 2x over 1. Think also as we do this, what are we going to use as our x value? What are we going to use as our a value? So in terms of x over a. So if you look at that as a fraction, x over a is equal to 2x over 1. So that means my x value is 2x, and my a value again is 1. My a value will not always be 1, it just is right now. So, derivative of y, I'm going to use my y prime notation. Derivative of sine inverse of something. Well, it's always 1 over, so I don't have to think about that. It's 1 over the square root of a squared, which my denominator was 1, so 1 squared, minus x squared. Our x amount was 2x. So this is going to be minus the quantity 2x squared. And then, like last time, is there a chain rule I can apply? We're doing the derivative of a sine inverse of something. Well, that something is 2x. What's the derivative of 2x? And that is 2. Clean it up again, and again, there's not a whole lot we can do there. That 2 can be put in the numerator. So 2 over the square root of, let's see if I clean it up, 1 minus squaring the quantity, 4x squared. And that's how I would leave it. Please remember, no, you cannot simplify that square root because it's a square root of a difference. It'd be different as a square root of a product, but as a sum or a difference, you cannot do that. Okay, one last example. Notice this one is asking us to integrate. Our whole lesson has been about taking the derivatives of inverse trig functions, and now all of a sudden we're being asked to integrate. And so what you need to figure out here, if we're being asked to integrate, which one does this match up with? Okay, that's the obvious connection if you ask me. Which one does this match up with? It's 1 over 1 plus x squared. So, and these are something you will have to work to recognize, okay? That's another important, it's good to know equivalence here. And hopefully you're realizing we can already eliminate sine, cosine, secant, and cosecant inverses because those all involve square roots in the denominator. The difference between tangent and cotangent, positive versus negative. So I would kind of think in terms of a guess. And my guess would be, is this a tangent inverse? So if we think about it, the derivative of tangent inverse of x. Let's see if it works. Okay, the derivative of tangent inverse of x, well, you go up and look. And again, you can think of it as x over a, but in this case, notice those ones. We're just thinking of this as x over 1. So derivative of tangent inverse is a, which a is 1, over 1 squared, which is 1, plus x squared. Chain rule says the derivative of x is 1, so nothing there. Does this match up? And it does. So all of that to say, what is the integral of 1 over 1 plus x squared dx? And the integral is tan inverse x. And what are you guys saying? Plus c. So that adds to your list of integrals that you are going to have to be able to recognize. How do I deal with those? So you'll see more of those in upcoming homeworks and lessons. Okay, your homework is lesson 64. We will do a quick check on that on Wednesday, and then review on Wednesday for test on Thursday is our plan. Make sure you get the homework 64 done. Thanks.